Today we're going to look at applications of polynomial equations. So we're going to do a few examples here. Of course, every example is a little bit different, so you need to make sure you read carefully and practice as many as you can. Okay, so here we have it. A box that holds an expensive pen has square ends, and its length is 13 centimeters longer than its width. The volume of the box needs to be 60 centimeters cubed. Determine the dimensions of the box. It is not necessary to list all the factors to this question, so you just can find your correct factor right off the bat. Now this, of course, I'm going to show you all the examples that don't give you the equation. If the example gives you the polynomial equation, then of course it's a little bit simpler, but based on your grade 10 and 11 knowledge, you should be able to come up with the equation for this. So we know that volume, of course, of a box is length times width times height. And then they give us some information about those particular dimensions. They tell us that its length is 13 centimeters longer than its width. Now, not to mention it also has square ends, so that means two of the edges are going to be the same, right? So we can start off by making our let statements. How about we let x be the width, and then it would also be the height of the box, right? And then, like they said, the length is actually 13 centimeters longer. We know that x plus 13 is going to be the length. And just to give you a visual, this is like a box like this, right? That would hold a nice fancy pen. Sorry, not that easy to draw on here, but you get the idea. This is x, this is x. This is our x plus 13. Okay, so we know then that we can go back to our volume equation, and we know that they gave us a volume of 60. Okay, we know that our length is x plus 13, and we have an x, and we have an x. Now, as with all polynomial equations, the method is expand, simplify, move everything to the right-hand side, and then we're going to need to factor that. So I'm going to do a little bit of work to expand and simplify and move things all over to the right. Okay, I'm going to start just with the right-hand side. You're going to want to rewrite that first as x squared and put it in front of your x plus 13. Okay, and then I'm going to start to move everything over. We're going to get x cubed. We're going to get plus 13 x squared, and then subtract 60. And you're going to need to start to play around with what are the possible factors of this to find your first factor. And that's what I mean by you don't need to list them all. You can go straight to your answer. If the application questions have crazy numbers that are really high and I wouldn't know, sometimes I will just give you a hint and give you the first factor, and then we would go from there. So I'm going to tell you right away that 2 works nicely here. So we'll start to go through our factor theorem just like we've been doing, using 2 as our first factor. So first we want to do our let statement. Let p of x be our polynomial. Okay, I know that p at 2 equals 0. You can check that. And that, of course, means that x minus 2 is a factor. And then I'm going to continue with my synthetic division. We know that we need a negative 2 out front here. We have 1, 13. We need a placeholder 0 in our minus 60. We're going to bring down the 1, so we get negative 2. 13, it becomes plus 2, which is 15. We're going to get negative 30. So 0 plus 30. Negative 60, and of course then we have our remainder of 0. So what did we find out then? We know that p of x equals x minus 2. Then we have x squared plus 15x plus 30. We're of course going to set that equal to 0 to solve. And we know that we get x equals 2. And when we simplify under this square root, we're going to get negative 15 plus or minus we're going to end up with the square root of 105 all over 2. And if you actually check these values, negative 15 plus the square root divided by 2, you actually get approximately negative 2.4, and then you get approximately negative 12.6. So now we need to go back and look at these answers. And if we were solving, of course, for x-intercepts, that would be fine. But since we are talking about dimensions of a box, these two values, of course, make no sense. So we actually have this as our one option for our dimension of our box, right? So if we go back to our original definitions, our original let statements, we see that then our box would be 2 centimeters by 2 centimeters by 15 centimeters, right? And we're going to omit those negative ones because they actually make no sense in this particular case. So let's go ahead and just write a therefore statement. Therefore, then, the dimensions are 2 centimeters by 2 centimeters by 15 centimeters. Okay, so that's example 1. Let's go on to number 2. Okay, example number 2 is this idea of the open top box constructed by cutting equal squares from the corners of a single cardboard sheet. And hopefully you have seen this picture before. I'm going to draw it. If you need a demonstration in class about how to get this idea, I can absolutely do it. So we have our cardboard sheet. That's, of course, 32 by 28. And we cut the little squares out. And we call that dimension of those squares x all around, and that sort of gives us the dimensions of our box, right? This line right here would be one of the base lengths of our box, and this one, and this one, and this one, okay? And the height of our box would be x if you can picture folding those up. So let's set up our volume statement. We know that, let's say v at x. The height of our box is going to be an x. Okay, this length right here, across, we can represent that as our 32 minus 2 x's. So 32 subtract 2x. And then this one right here would be our 28 minus 2x. Okay, and very similar, I'm going to go through it as quickly as possible, very similar to the last question. We're now going to set up our equation, and then we're going to move everything to one side and go ahead and factor to be able to solve. So I'm going to do a little bit of expanding here. Okay, when I expand this polynomial out, I should get 4x cubed minus 120x squared plus 896x. And then I'm going to move my 1920 over, and I can take a 4 out of it, and I'm going to get x cubed minus 30x squared, and you can do this on the side if you need to see it, plus 224x minus 480. Okay, now that's quite a large polynomial that we do have to use the factor theorem for, but I can quickly see that a 4 is going to work here. So just like we did before, we're going to say p at 4 equals 0. Okay, therefore our x minus 4 is a factor. I'll set up my synthetic division. We have 1, we have minus 30, we have 224, we have negative 480, we have 1, negative 4, we get negative 26, we're going to get 104, we're going to get 120, conveniently we're going to get negative 480, so a remainder of 0. Okay, so what do we have so far then? Therefore then, let's go straight to our equation. We have 0 equals x minus 4. We actually have a 4, common factor of a 4 in front that we had pulled out just so that it was a little bit easier to divide. And then we're left with x squared minus 26x plus 120. And that continues to factor. I get 4x minus 4 x minus 20 and x minus 6. Okay, and if we continue through and we try to solve for x here, we can see that we have three possible solutions. We have x equals 4, we have x equals 20, and we have x equals 6. Now, just before we go any further, think about that x equals 20 for a minute, because if you look at our picture, if x was actually 20 here, then we wouldn't actually have a width or a length or whatever you want to call it for the box. So we can see that that would result in negative dimensions. So we're actually going to ignore the x equals 20. But x equals 4 and x equals 6 look like they work. So then we would have two sets of dimensions. We would have the one where x equals 4, so that's the height of the box, and then we would have the one where x equals 6. Okay, and you would just need to go back to the original definitions to find out what the other dimensions are. With the 4, you would actually get a length of 24 centimeters, and then you would get a width, just going to continue here, of 20 centimeters. And then with the height of 6 centimeters, you would get a length of 20 centimeters and a width of 16 centimeters. So you have two sets of actual possible dimensions there. These, of course, would be your heights. And there we go for that question. So let's try one more. So this is a bit of a different question where I tell you the roots of a quartic function, and notice we have two real roots here and two complex roots, and I give you a point and we're going to actually come up with the equation of that. So this one's similar to what we were doing before, but now we have these complex roots in here that are conjugates. So let's go ahead and see if we can at least set it up. So right away from the beginning we know that f of x equals a. The first part's easy. We have x minus 2. And then we have x plus 3. Okay, and then we're going to deal with our complex ones. Exactly the same. We would have x subtract 3 plus 2i. And then we would have x subtract 3 minus 2i. Okay, and in order to do this, you're actually going to have to expand these out, and I'm going to start by doing these complex ones right here, because we do know that as we simplify and we expand this, if we get an I squared, we know that our imaginary numbers kind of disappear. So let's do a little expanding. You can expand the first two together, the first two binomials to get a trinomial, just to make it look a little simpler. So we're going to end up with plus x and then minus 6, and then I'm going to work on this second part here. Okay, so the first thing you might want to do is just simplify how we write them. So we have x minus 3 minus 2i, and then we have x minus 3 plus 2i. So we're multiplying a trinomial by a trinomial. Just need a little bit more space here, so we'll write this as small as we can. Okay, and now let's go. First we have x squared, then we have minus 3x, then we have plus 2xi. Okay, then we're going to deal with our negative 3, so now we have negative 3x plus 9 minus 6i. I'm going to continue on the next line. Then we're going to have negative 2xi. Then we're going to have plus 6i. And then we're going to have minus 4i squared, and it does get a little bit long, but let's take a look at that. Okay, notice we have a plus 2xi, minus 2xi gone. Notice we have a minus 6i plus 6i, and all that we're left with is this imaginary number, which we know if we replace that I squared with negative 1, we actually end up with all real numbers. So look at that. We have a x squared plus x minus 6. Then we have x squared. I'm going to combine like terms there. We have a minus 6x. And then let's look at our actual numbers here. We have 9. And when I sub in negative 1 here, we get plus 4. So we actually end up with plus 13 when we simplify that all out. Okay, and again, this is a quartic polynomial function. And think back to when we did these and we actually solved for the roots. You never saw the imaginary numbers in the original polynomial function. So the fact that it's all real just means that it's a normal polynomial, but it had some imaginary roots. Okay, and then of course we can solve for a just like we did in class by subbing in that 1 point that they give us. And I'm going to let you go ahead and finish that. You can let me know what a is tomorrow in class. See you then.